Everybody, I'm Becky Moore. I'm the chair of the advisory council of the Museum of the White Mountains. Can you all hear me?
Yes.
Everybody hear me? Great, good. So it's my very great pleasure this evening to stand in for Marcia Schmidt-Blaine, who I'm sure many of you know, Professor Emerita of History from PSU. Marcia is probably will be signing in, but she's taking care of grandchildren and probably putting somebody to bed. So Lisa, I'm delighted to be here to introduce you. I've been lucky enough to serve on a panel with Lisa a number of years ago, and I think she's an outstanding speaker. So Lisa, thank you so much for taking the time to join us this evening and share with us your research on the impact of climate change on New Hampshire's lakes. I think each one of us has a lake that we love in particular, that we care for and we worry about. And this is an opportunity to hear the results of Lisa's research. I also want to say in particular that this year on Mountain Voices, we're showcasing PSU faculty and their research. This is a wonderful opportunity for us to know what they're doing and what they're thinking about and how valuable they are to us here in the region. Lisa's research, as some of you may know, focuses on how climate interacts with other elements of change, such as natural catastrophes and human disturbance, and of course, long-term trends, big long-term trends like sea level change and tectonics. So we're also fortunate that Lisa's training has been from across the country, from BS at the University of Arizona, an MA from, where did you do it? University of Maine, and a PhD from the University of Colorado, which means that she is able to help put New Hampshire's or the White Mountains lakes into a much broader perspective of the entire country. And I think that's very important. And before I finish, Rebecca may remind us at the end, I want to remind you all that our December speaker is going to be Dr. Thomas Stoughton, who's going to be speaking on mushrooms in the White Mountains region and sustainable harvesting. So without further ado, Lisa, thank you so much for doing this. And we look forward to what you have to say this evening.
Thank you. And I have just one question for Rebecca. Once I share the screen, are you going to still be able to see people trying to get admitted or? Okay. All right. So I'm going to start with the screen sharing. Can you all see that? Okay. Thank you very much for that very gracious introduction. And I'm really delighted to be here to give you all a chance to learn about and hear what I've been doing because I think it's important. And a lot of my research has been driven by requests from within the community. Lake associations across New Hampshire and in Maine have sought advice, and I've ended up working with them in cases to try and find some answers to do the lake management and reach the goals that they want to. So this work has always been enabled by students, both graduate and undergraduate students. It's almost impossible to do this alone. So I want us to consider, what is a lake? What do we think about when we think about lake qualities and why we value them? Certainly it's a place to visit. It's a place to recreate, do our sports, but it's also a place of contemplation and peace, somewhere we go when we just want to crowd and be somewhere really beautiful. Lakes have other roles, however. Many people rely on them for water or for their livelihoods, whether it's old-time logging and rafting them across to a different shore or to a lumber mill, or renting cottages and making a living from the cost of those rentals in this beautiful tourist area, or for food itself. And, you know, I think probably most of New Hampshire's lakes, people don't spend a lot of time fishing them out of need to fish. But in many places of the world, that's what those clear freshwater lakes offer to the local inhabitants. And there's also hydroelectric. This is in the lower right is a picture of the dam coming out of Newfound Lake. And it still functions in a hydroelectric capacity, even though we have many more sources of energy now than we used to. But lakes are also the bottom of their watershed. They are the hole or the basin at the end of the slope, so that everything that's on the sides of those slopes or the watershed eventually ends up headed towards the lake. And once it reaches the lake shore, it usually heads to the deeper part of the lake, which is where I take a lot of my sediment cores from in order to capture that entire record. But that means it's a collecting basin for everything, good and bad, human-made and nature-made, and the chemicals that are associated with those. So as a result, inputs, different sources, if those inputs increase, whether it's because of higher intensity of rain carrying things or higher intensity of development with more stormwater runoff, or climate change, bringing debris and things to the lake, we find ourselves at a place where our lakes are being stressed from a lot of different sources. In the lower left here is a picture of a Cyanobacteria bloom from, I think, 2015, which we happened to catch in mid or late October, actually, because it was a warm fall. Here's a sediment plume. I'm not sure which lake this is. And this picture on the far right is actually not New Hampshire. It's a lake in Turkey that I was studying, but it shows you, it gives a good indication of what happens when the lake shore gets very mucky and unappealing and overgrown. So I apologize for all of the text on this slide, but it's important, I think, to highlight what lake protection is supposed to be accomplishing. It's about improving the quality or preserving the quality that exists. Water quality, primarily drinking, shoreland quality for property value, just visual appeal, but also lake access and the impacts of the water, the shore on the water and the water on the shore. And water quality or watershed quality for controlling water runoff and erosion control and just basic ecosystem services. So, you know, this presentation is really about an assessment of how New Hampshire lakes are doing based on the research that I've been engaged in. And there is a assessment that is ongoing now, updated on a regular basis from newhampshirelakes.org. And I have the link up here, so you can go peruse into that. But those are snapshots of year to year. And based on those snapshots, what we can understand is that New Hampshire lakes continue to be some of the best ones in the country. They're very clean in general, they are healthy. There's not a lot of significant problems in most of the lakes. And we continue to be a destination place for people who are seeking those lakes. If you have ever traveled outside of New England and into the Midwest or into areas lakes are more impacted, or you just don't have that beautiful, deep blue, clear water, you can come back to New Hampshire and realize, oh, these are the lakes I really want to be swimming in. I didn't really want to swim in those lakes. Honestly, after living in New Hampshire, I have trouble swimming anywhere else. However, there's some bad news. And the bad news is that the number of safety advisories, water quality safety advisories, is rising each year. The clarity of the water in the lakes, that's how far you can see down into the water column has decreased in about 16% of the lakes. 18% of New Hampshire's lakes have warmer surface waters and are experiencing ice out that's delayed by more than 2 weeks from the period of prior to 1950. And there are residual problems that continue to crop up, such as lead and DDT in Squam Lake was something I just recently studied. And these things are they were old problems. We fixed them with regulations, but they're still there in the watershed, and they do still make incursions into the lakes. More than 90% of the water quality problems in New Hampshire are caused by polluted runoff. And that's water that is impaired by coming into contact with road salt or through fields spread with fertilizer, or with animal waste, or soil erosion. And that polluted water and polluted groundwater, which is mostly going to be coming in from septic systems. That's the most common source of polluted groundwater, but also fuel spills, and then salt that has accumulated in the groundwater, because road salt has been applied for such a long time now that it's not just a surface runoff issue, it's also in the soils. And every time you get a rain event or a melt event, it flushes some of that soil salt out into the lakes also. So now I want you all to take about 5 seconds and just picture a lake, any lake you want, just visualize the lake. And I'm wondering, did anybody imagine anything beneath the surface? I don't know if anyone's going to answer, but I'm going to assume that most of you did not. Because what most people usually see and think about is that surface layer. You're looking down on the lake, or you're floating on top of the lake, or you're swimming in that surface layer of the lake. That's our most common experience. It's what's in everybody's photos. And it's really easy to forget that that is just the skin of the lake. And that what gets affected by the runoff and by climate change, by lake level changes, and by pollutants coming in is the rest of the lake. It's the much greater volume of water. It's the sediments that are near shore and in the deep basin, and it's the interaction of all of those together. So how do we go about understanding what is beneath the surface? We have several ways to measure. What we know now, and we've known for decades, is that lakes tend to, especially lakes in New Hampshire, the lakes tend to stratify, so that in the summer you get a warm layer on top, and then there's a very steep temperature change we call the thermocline, and then cold layer on the bottom. And that cold layer varies in thickness depending on the shape of the lake and the depth of the lake. In summer, the surface waters can warm up to 80 degrees Fahrenheit, and the bottom waters, however, don't get that warm because they are trapped in the bottom by the thermocline. So they may warm up to 40 degrees, but that's about it. In the winter, the coldest water is actually at the surface. It's near the ice layer, or where the ice is trying to form. And interestingly, the bottom water is about the same temperature in the winter as it is in the summer. So these behaviors of lakes to stratify affect their ability to hold oxygen, their ability to mix, and the overall water quality. The way I have gone about studying these aspects of lakes is by setting out temperature moorings. And so what you see here in this picture on the right, this yellow object is a buoy that sits underneath the surface of the water, but it floats. And it's held to the bottom of the lake by this set of weights on a chain. And then in between the buoy and the weight is a cable with a temperature recorder that hangs every, like 1 meter apart. So 3 feet apart from each other, there's a temperature logger that wakes up every 15 minutes and takes the temperature and then goes back to sleep. And this mooring stays in the lake, underneath the lake ice and all year long. And I just bring it up in order to download the data. This is what it looks like in a schematic. It's that buoy is designed to be underneath the draft of the motorboat engines, and so they don't interfere with boating and they don't create a safety hazard. And then when we want to collect this buoy, there's a radio transponder in here, and I send a signal down, and it causes these two parts of the buoy to separate from each other, and one part pops to the surface, and I can retrieve the whole string. So this is the most intense data you're going to see on this presentation. But this is the collection of 6 years worth of winter summer temperature records from Squam Lake that I put in 2014, and I pulled out for the last time last summer during the middle of COVID. And the equipment had basically reached the end of its life. So even if COVID wasn't creating a problem, I would have probably had to stop this research at some point until I could get more funding. But what we're seeing here is on the left axis is water temperature. So freezing is, and it goes up to 30 degrees. This is in Celsius. And so 25 degrees is about 75, 72 degrees, a nice summer temperature. And then along the horizontal axis are the dates. And, you know, I could have put these dates at any place, but each one of these is about a week apart from each other, I think. Maybe it's 2 weeks apart. But it spans that entire 4-year period, with the most recent one being on the far right. And then each one of these represents one of those little black temperature loggers sitting at a particular location on that cable and the depth that it was sitting at that cable. So these depths on the right are actually the depth above the lake bottom, because the lake levels change. So the top of the lake varies a bit, and the only fixed place I could have to measure depth was from the bottom. So it's a bit weird, but these are measured up from the bottom so that the light green ones are near the lake surface. And then as you get into the oranges and purples and reds, those are deeper. And then the blues and grays are near the lake bottom. And the black line is right at the anchor. So what we see is a whole series of seasonal changes in response to what's happening with the outdoor temperatures, the atmospheric temperatures. And we've got winter cold temperatures and summer warm temperatures. And then we see spring and then fall. And so each one of these blips is a full year's pattern of temperature changes within Squam Lake at this one particular site, with the arrow indicating, for instance, the range in temperature on that one particular day for that one particular 15-minute interval. That's the spread of temperature changes across there. So we had a peak of about 27 degrees, and the bottom water there was about 6 degrees Celsius on that particular day in late July or early August of 2015. So I don't want to belabor this point, but this is a very rich data set that helps us understand how the lakes are changing temperature over time. And one of the things that I hope to capture with this is a sense of how lakes are responding to changes in things like shorter duration of ice cover. And one of the fascinating things, if we go back to that prior slide of what winters do, where the bottom water is warmer than the surface water. We see that here in most of these winters, where the temperature profile of the summer is completely inverted, and the warmer temperatures are that black line right at the anchor, and then the temperatures are as you get towards the surface, the greens, for instance. And that sets up in every single year with one exception. The length of these is also of interest in terms of how long this, what we call reverse stratification, exists. But I want to focus on that one exception year, because I think it's a trend of what might happen in the future. This is just a blow up, that one interval. And what happened in that particular winter is we didn't get ice cover on Squam Lake until about January 10 or so. So it was a very warm fall. And when you don't have the ice covering the lake, what happens is the water is just constantly giving off its heat. Lakes have a lot of stored heat in them that they gain all summer long. And the only thing that stops them from losing that heat is to put an ice cap on top, just like you would put a lid on a cup of coffee to keep it warm. Putting a lid, and even an ice lid on top of a lake, keeps that water from losing all of its heat. You don't have that lid, it just keeps losing heat, losing heat, losing heat. And that's what we see in this trend all the way down over almost 2 or 3 months of time. It lost heat until the entire lake's temperature was about 1 degree Celsius. So that's very close to freezing, and that's extremely cold habitat for fish and other living organisms in the lake, actually, because they're used to it. They're used to those bottom waters being no colder than about 4 degrees Celsius. So, you know, when you go from 40 degrees Fahrenheit to near 32 degrees Fahrenheit freezing, that's a really critical difference in terms of the ability of that lake and the life in that lake to function. So I suspect that it impacted fish stocks, at least. I talked to Fish and Game and learned that they don't monitor the survival of the fish that they stock in the lakes. They just don't have the capacity to do that. And nobody else is doing that on a regular basis. So there's no way of knowing how much impact that particular year had on these lakes. But, you know, as our falls get warmer and the period of ice cover is reduced, we're going to see more and more of these events of the bottom water or the whole lake water becoming much colder than it normally would. So that's what we can tell by studying the lake water and the surface of the lake. But there's a lot of very interesting things to be gained by looking actually into the mud. We can see the history of the lake by looking at the sediments that have accumulated in the bottom of the lake. And the easiest way to do this is through a device we call a corer. And this is a picture of what a short corer looks like. It's just a plastic tube with some weight on it and attached to a line that we put this whole thing over the side of a boat or through a hole in the ice. And this one has a little weight on it so that we can hammer it a little bit if we need to, but we let this free fall into the sediment and then tap it if we need to until it's filled with sediment. And then we just pull it up. And this particular type of corer has a little device at the bottom, a little ball that plugs into the bottom and prevents a lot of the loss of sediment that might occur as soon as you lift it out of the water. So anyway, this is how we go about doing it. It's relatively easy. It only takes 2 or 3 people. I have done this from a canoe, although it's more from a canoe. And you can do it during the winter time when the lakes are frozen too. So this is a core from Newfound Lake that we collected on Super Bowl Sunday, actually, in 2018. And one of the things that we have learned from the study of these sediment cores from a lot of these different lakes, so each one of these colored dots is a different lake that I've studied, or a site in the lake. So there's Spofford Lake, Keezer Lake, Squam Lake, Ossipee, Wentworth, Deep, let's see, there's a bay in Wentworth Lake, I think Grant's Deep or something like that. And then the deep basin of the lake, Webster Lake, and Pleasant Lake. And I measured the chemistry of the sediments of all these, and I dated all of these cores so that I can, this bottom axis is age. So 2020 or 2010 or so, 2015, 16, 17 are about the newest cores that I have on here. And what we see is that the background levels of lead in the sediments is very, very stable until about the early to late 1800s. And then it starts to climb a little bit. And it really starts to climb right about the time that the combustion engine introduced motorboats and cars to our country. And there's a lot of atmospheric fallout of that lead, but also there's probably some spillage from local sources of motorboat fuel and stuff. But every single one of these lakes shows an increase in lead after 1915 or so. But the good news is that we see that because of the regulation that took the lead out of gasoline, all of these reach a peak around the 1970s or early 80s and then drop off. There's one exception to that, Spofford Lake in this hollow circle here. It did reach an early peak and started to drop off and then climbed way up. And it turns out that there's a suspected fuel spill at one end of the lake where we happen to take our core. And the good news is that that just lasted a few years, and then those levels decreased again too. The other thing that we can learn from these lakes is how much material is settling into the bottom of the lakes. And one of the materials that's most important in understanding water quality and the future health of these lakes is what we call the organic content. It's the measured by a method called loss on ignition, where we just a sample of the mud and we dry it and then we burn it in a furnace, and we measure the difference in weight between the dry sediment and the burnt sediment. This gives us a sense of how much carbon or just generally organic material is being collected in the lake bottom. And these axes are all set up so that the older part of the core is to the right, and the left part of the younger part of the core, the newest sediments, are to the left. So 2000, 2010, 2020 are the youngest sediments in most of these. And the name of the lake that is contributing this data is written on the title. So what we see here is that almost all of these lakes have an early period where there's a peak in loss on ignition, or this organic content. Wentworth Lake has a very high peak, and this, I'm not sure what this is being caused by, but I suspect that this might be a logging or a deforestation measure. Maybe there was a sawmill on the lake that was dumping a lot of organic material in. Squam Lake has a little bit of that blip too. Pleasant Lake has that blip over here. We see it a little bit in Norway Pond here, and here, and then Keezer Lake here. So that's not unusual. We know that there was significant land use changes in New Hampshire, across all of New England actually, that involved deforestation and shredding and loss of organic material. And a lot of that ended up in the lakes. All of these lakes show a recovery period between about 1850 or so and 1950. And then the organic content starts to rise again. So this later rise in organic content is a concern because a lot of these lakes are under lake management, and lake conservation efforts had begun by the time this rise started. And it's a fairly steep rise in all of these lakes. If we look at just the post-2000 period, the last 20 years has been a time of significant increases in the organic material that's accumulating in the bottom of these lakes. So a bunch of questions come up. Where's this organic matter coming from? And why does it matter? What's the impact of this happening? The question about where it has come from, there's a couple of options. Generally, we limnologists, people that study lakes, tend to assume that if organic matter increases in a lake during a warm period of time, it's because there are algal blooms that are happening in the lake, both microscopic and macroscopic algae, that is just doing very well because of the warm water, and it's thriving and it's growing. But there are also factors that can contribute to those blooms besides temperature, and fertilizer is a really big trigger of sudden increases in algal growth in lakes. And so whenever you see a sharp change like that, one suspicion is that there may be fertilizer pollutants coming into the lake, and they're stimulating those kinds of algal growth situations. So in order to control that, one of the first things that a lake association would want to do is to start measuring phosphorus and nitrogen, and looking at sources that might be contributing to those and try to reduce those. A big culprit is leaky septic tanks. So as people settle around the lakes, as the lake development occurs, as the population of summer and winter residents around lakes increases, you're going to get more and more septic tanks that are needing more and more maintenance, and that maintenance might not be occurring. However, one problem with that explanation for the lakes that I showed you is that many of them actually had pretty good report cards as far as phosphorus and nutrient levels, and there was no real indication that they were experiencing this kind of fertilization effect. And so, the other option of where this organic material could be coming from is that it might be coming from land, and there are lots of possible sources on land. I mean, all the trees around the lakes are dropping leaves. People have a hatred of leaves in their yard, and so they dispose of them, and some of them may be disposing them into the waterways and lakes and ditches, which ends up into the lake. The same thing with grass clippings. Every time the lawns are mowed, where do those clippings go? And there are still stockpiles of sawdust, we know, around in certain areas. So these could all, dumping of those could all create the same kind of signal if it's happening on a lot of properties around the lake. But another thing that could be contributing to this, and maybe a bigger factor, is the erosion of the shoreline, because soil in New Hampshire has a lot of organic material in it. It's got all of those leaves and roots and stems and all of that stuff that would have created sawdust if you cut the tree down and chewed it up. So every time you have a plant growing in the soil and then it dies there, it contributes that organic material to the soil. And then when that soil erodes into the lake, it's bringing that organic material with it. So it's possible that that is one source. Now, the why does it matter part, when organic material comes into the lake, any water body, it will sink eventually, and it will start to decay. And interestingly, when organic matter decays, it uses up oxygen. It takes oxygen to do the decay process, and it takes it from the water because that's where that decay is happening. Decay on land takes oxygen out of the air in order to do that, but underwater, it takes it from the water. which means that there's less oxygen in the water for other things that need oxygen, like fish or any sort of invertebrate, or basically anything living in the lake that's breathing the water and taking nutrients and gases out of that water. They need that oxygen. So decaying organic matter can use up all the available oxygen, creating a situation that's known as hypoxia or anoxia. They both are basically the same term. And it can create what's called a dead zone for life. So dead zones are just areas where there's not enough oxygen to sustain life. They can be very small, or they can be short duration, or they can last long enough to cause massive die-offs. A fish swimming through a dead zone is not going to stay there. It's going to change its location. But if it can't change its location because that dead zone is too widespread or in too thick of a water mass, and it can't live in the temperature of the water where the dead zone isn't, that fish is going to be extremely stressed. And so we end up a lot of times with fish kill. The other thing that happens when oxygen is gone is that decay, if there's still more organic matter, that decay will still continue. Only this time, instead of using oxygen, it'll start converting sulfur and other elements. And one of the things it does is that creates sulfur dioxide, which is that rotten egg smell. And it can also produce methane instead of carbon dioxide as an emission. So one issue with having low oxygen levels in lakes and high levels of organic matter coming in is that these lakes become sources of methane to the atmosphere. The other thing that's tricky about low oxygen conditions is it changes the chemistry of phosphorus and makes it easier for phosphorus to be released from the sediments and go back into the water column. So if you had, let's say prior to the 1960s, when everybody was using phosphorus enriched borax to make their clothes bright and white, all of that phosphorus that was in the sediments and washed into the lakes and became part of the lake sediments at that time, that phosphorus from the 1960s can be remobilized when that lake bottom becomes anoxic. And then that contributes to the phosphorus loading of the lake. And so in this way, lakes can self-fertilize. And this is an issue for management. Once a lake starts having this cycle of phosphorus being extracted from its own sediments and then causing algal blooms, and then those algal blooms die and go to the bottom and then rot, and then that causes more phosphorus to be released. You can see that this is a rather nasty cycle. And so controlling this can be very difficult. But I'm going to propose something that nobody ever likes to hear. I haven't met a lake association yet that's happy to entertain this idea, but I think it's a venom. And that's the idea that, we've done a pretty good job of controlling nutrient loading to lakes. We're very conscious of those issues now. Many lake associations and watershed associations have been working on stormwater runoff and controlling erosion and getting the word out not to fertilize down to the water level. But one of the things that hasn't changed is the amount of boat use. And the sale of boats, for those of you that are old enough to remember, not everybody used to have a boat. They became affordable in the 1980s, 1970s and 80s, with the onset of like fiberglass boats and cheaper motors, and also access. I think there were more access points. And so the boat use and boat sales in the US grew tremendously. And so this is a chart of the total number of boats, motor boats, registered in the US between 1980 and 2018. And you can see how quickly it rose. It went from just over 8 million to upwards of 12 million boats in the US. And wake boats became they were first developed in the late 1980s, and they've become increasingly popular in the last 20 years or so. So in order to understand how motorboats affect lakes and might be contributing to the lake health, you have to understand that most lakes have a prevailing wind condition or direction that pushes wind-driven waves. So those are the natural waves on a lake in one direction for the most part. And those waves go from upwind to the downwind side of the lake, and then they batter that downwind shoreline. And those shorelines, since the lake developed, those shorelines were going to have been eroded and all of that fine sediment removed, so that those will be where you see your bedrock shelves and big boulders exposed. But the rest of the shoreline that's not downwind would be relatively protected because it doesn't receive that directional kind of wave development. When you add boats, and those boats go everywhere and in every different direction, they are generating waves that are impacting every square area of that shore. And it doesn't matter if it's the prevailing wind direction or not. Those waves are chaotic and they're going in a lot of different directions. And so the entire circumference of the lake has become of a lake that has motorboat use is exposed to fairly high energy waves on a regular basis during the summertime at least. And so the entire shoreline becomes an erosional surface, not just the downwind shoreline. The other thing that can affect shoreline stability and the amount of material coming in is changes in lake level. So I've just drawn a very simple model lake here with one standard lake level with the black line indicating where the shore is. And if you change the shore by lowering the lake level, you create a new shoreline. And that new shoreline that used to be underwater is now exposed to the highest energy of those waves. Similarly, if you raise the lake level, you've also created a new shoreline, and you have exposed that new shoreline to wave battering. And so changes in lake level, which usually modify themselves. So like if you get a rain event and the lake level goes up a foot, usually within a week or two, that lake level has dropped back down. But managed lakes, especially boats managed or lakes managed for motorboat use, are often kept at their highest reasonable level in order to allow access to docks and to bury rocks and reduce numbers of hazards that might cause in the lake. And so they've created a new elevated shoreline, and that new shoreline is being attacked by motorboat waves as well as the new level of prevailing wind in the downwind direction. So we're seeing a lot more potential for loss of shoreline into the lake with the organic material that it carries within it. So I think I had a section here that I called Lake Science News, but I think, I've used up 45 minutes and I would like to have time for questions and answers. So I'm just going to skip to the end here and give the take-home messages. And those take-home messages is that New Hampshire's lakes are changing. They're happening faster now than 20 years ago. There's temperature increases related to climate change that are certainly pushing some of those changes. Lake level and motorboat decisions are enhancing shoreline erosion and the input of organic material. We have residual pollution effects from as long as 100 years ago, but natural recovery of those is happening, so that's good news. And conservation of the watershed area around these lakes can impact or reduce the impact of many of these changes and help them out. What I didn't cover that I skipped over was what's happening globally. And basically, these trends fall right in line with what is being seen in lakes all over the globe. So this is not just unique to New Hampshire. These changes in organic content, the changes in the amount of dead zone, the changes in the way the lakes are stratifying and using those nutrients, that's being repeated all over the globe. And so, you know, these are not just New Hampshire issues, they're global issues. And, you know, there's not going to be any one solution, but certainly protecting the lake as much as possible and continuing to monitor your lakes is the only way we can keep track of these changes. So I worked with a lot of different groups here. I didn't show the data from all of them, but I very much appreciate the lake associations that have reached out to me, with me, and the students that they supported and the amount of research that they engendered. So thank you very much. I'm going to stop sharing now so I can see all your faces again. Are there any questions?
Thank you, Lisa. That was absolutely fascinating. I know that we have a couple questions. Everybody, you're welcome to add your questions to the chat. I'm going to read them out to Lisa. Why don't we go back to the Squam Lake water temperature? I know that there are a couple questions about that. A question from Nancy. What happened in the winter of 2016 where there is no data?
Well, the gaps where there is no data, it wasn't the whole winter, I don't think. Let me share my screen again and I can go back to that. Maybe I can go back to that. (2016). So I think you're thinking maybe about here, which is a summertime gap, or here. These were times when I had to lift the buoy and there was problems getting that back into the water, either because the wind came up when we were retrieving it and we couldn't hold anchor, and then I couldn't get boat time to get back out. Sometimes, like this longer gap in 2019, was because I had to change the batteries, and that meant ordering them from the company and getting them in. So that's, hopefully that was the question that answers your question.
Yeah, I think so. That's great. Let's combine maybe this next question. Does forest fire history show up in your cores? Oh, wait a minute. Sorry. No, let me go back a little bit further. Oh, no. Let's go back to the core question. Does forest fire history show up in your cores? And does the increase of organic material also coincide with the advent of sheep fever and clearing of land for raising sheep, as well as runoff from the manure?
Those are great questions. We could detect forest fire history. Charcoal is very easily preserved in the sediments, and it's just a matter of looking for it. I didn't have the capacity, the student capacity, basically, to look at each of those samples for forest fire. But if somebody was interested in the history of forest fires around their lake, that would be easy to do with this kind of method. And the other question about the sheep boom in 1830, definitely that had an impact on both erosion and organic material coming into the lake. But that went away towards the end of the 1800s. And by the time industrialization was drawing everybody off the farms and into the cities, basically those lands were starting to reforest, and that was stabilizing erosion and reducing the amount of material coming into the lakes.
So cool. Another question about cores. Winnipesaukee turns over every spring, which I assume does a lot of mixing. Does that not happen with these smaller lakes that you have studied?
So Winnipesaukee is definitely the biggest of all of those lakes. But these are pretty big lakes by the scale of how small lakes can be. I mean, New Hampshire Hampshire has about 1,000 lakes, and many of them are less than 5 hectare or 5 acres in size. So yeah, turnover in spring and in fall happens in almost all lakes, but it can be minimized by that stratification. And what I saw in those temperature profiles is that difference between the time of inverted temperatures, where the bottom water was warmer than the top water, when that ended and when the summer stratification started, was sometimes as little as 2 weeks. So usually by late April, all of those lakes that I've studied show signs of restratifying and setting up for their summer stratification, which means that spring mixing is not very intense. The fall mixing can happen over several months, but that spring mixing, I think, doesn't occur over as long of a period. And I saw these same trends in Icelandic lakes that I studied too. So this was not just unique to Squam and Newfound.
Awesome. Let's do this question from Eric and Judy. Have lakes been studied to see how shoreline protection and setbacks have impacted the shoreline erosion compared with land in conservation?
I so wanted to do that study. I made a proposal to do that at Squam Lake when the Shoreline Protection Act went in. I said, this is the best time to study the value of that. No, I don't think that's really happened. And that would be a really effective way of showing the value of that regulation.
All right. Looks like you need to connect with Eric then, talk about that a little more. From Charles, all very interesting. What methods do you use to date sediments in the cores? What are common rates of deposition, or I think per year, decade, or century?
Okay, so all of the cores that I showed you were dated using a technique called lead-210. So it's a radioactive isotope that the lead comes out of the sky in radioactive form. It's created in the atmosphere, it settles in the lakes, and then as soon as it's no longer in contact with the atmosphere, you have less and less and less in the sediments with each year. And so you can use that reduced amount of radioactivity over time to date the core. And so the sediment accumulation has been, I mean, it varies from lake to lake, but it's usually about an inch a decade.
Interesting. Next question from Anne. I think this is the last question I have on my chat. So anybody, if you have any questions, definitely add them. From Anne, what is the best way to monitor for septic leakage and to take fast action? Who as well as how?
So that's a sensitive subject because people don't like being told that they have to clean out their septic tanks or be caught with a leaky tank. One way to do it is to go in and look at the permits and see when those septic tanks went in, and then just send reminders to the homeowners saying, hey, we see you built your house in such and such a time. Normally, your septic system should have need to be checked or cleaned out, every, whatever it is, 5 years or something like that. But another way, if you suspect that there are like rental houses or something, like old cottages that get rented out all the time, and if there are ways of going along the shoreline and actually taking samples of the sand or the shore sediments, you will almost certainly see higher levels of E. coli in those sediments compared to neighboring areas where there is no leakage, because E. coli is going to be a really good indicator of a failed septic system.
Good to know. All right, that was the last question that I have on my chat. Again, if anybody wants to add a question, we have a couple more minutes if anybody would like to do that. I have to say, this has been really interesting. I grew up in New Hampshire, and I definitely have my favorite lakes, and it's good to know and kind of find out all about all of these things. Let's see.
One of the things that I didn't talk about that was part of those new findings, those science findings, is that there's an increasing concern about algal blooms that are happening on the bottom of lakes. So these very clear lakes like Lake Tahoe and other lakes that are famous for their water clarity, they're having algal growth in the bottom of the lakes from an unknown cause. And so what they are, some of the things that they're thinking is happening is that nitrogen is coming in from the watershed, and because the lakes are clear, that nitrogen gets absorbed in the bottom sediments, and then the light from the sunlight is able to reach those bottom sediments. And there's this type of algae called filamentous algae, or filamentous algae blooms, FABs. Everything has an acronym, right? So the FABs are the new worry. So if you have a clear lake that seems to be getting algal growth in the bottom, you might look at that and take a sample of that in to see if it falls in this category.
Good to know. All right. Well, thank you so much, Lisa. I think with that, since we don't have any more questions, we will end it there. That was just really wonderful. And thank you all so much for coming and joining us. Thank you, Lisa, for giving such a great talk. Everyone, I will be sending out an email tomorrow with a video link for the full video if you're interested in it. And we look forward to seeing you for our December talk, and that will be more information on our website and in our email. So
thank you very much.